Here's the problem. Let's put systems into Matlab, only it's going to be a very high order system, like a 10-stage RC filter. There's a couple ways to input systems into Matlab. If I have it in factored form, or transfer function form, I can put that into Matlab as follows. I can say G is the transfer function, numerator polynomial is 10, denominator polynomial is in powers of s, 1s to the fourth, 10s cubed, 35s squared, 50s, 24. And voila, there's g of s. If it's in factored form, I can input it in terms of poles and zeros. Here there are no zeros. Poles are at -1, -2, -3, -4. Again, on top is 10. Given one form, I can go to the other. G is in now factored form. Let's say what's the transfer function of G. And there it is. I can also input in state space form. State space is actually much more convenient in this class. Case in point, if I had this RLC circuit, I want to find the transfer function from V in to V out. What I want to do is input it in state space form. First, I want to write the coupled differential equations. The states are the energy in the system. That's the current in the inductor, where the energy is 1/2 Li squared. Voltage on a capacitor, 1/2 CV squared. The equations for an inductor is V is L di dt. The voltage across the inductor will tell you the change in current. For capacitors, I is C dV dt. The current into the capacitor is the change in voltage. That puts it in state space form. So again, assuming if you write the equations for the voltage across the first inductor, I get equation in terms of the input and the voltages and currents, the states. Current on the second capacitor, likewise. Let's go up a bit. This voltage is Vn minus this voltage, which is 10I1 plus V2. This current is the current in, I1, minus current out, I3. This voltage is V2 minus V4. And this current is I3 minus this current, V4 over 20. Plugging in numbers, in solving for the derivative, I get the change in the states, or a function of the states in the input. Putting in matrix form, I get this. This is the state space model. The output is the voltage across the last capacitor, so the output is the fourth state, V4. There's my A, B, C, D. Once I have A, B, C, D, I can input that into Matlab. Here's your A matrix. There's B, C, and D. Now put that in your system as SS. G4 is state space, A, B, C, D. Here's your A, B, C, D. And voila. More useful, once I have the system in Matlab, using the correct system, I can sit there and say, now what's the transfer function in terms of zeros and poles? I can say what is the transfer function in terms of multiplied out polynomials. I can take the step response. Try that again. There we go. And you can find the step response. Again, way faster than you can find it by hand. Where state space really shines is on systems like this. Here I have a 10th order RC filter. It looks rather daunting, but everything's the same. So if I take any given node, the current to the capacitor, C dV dt, is the current IA plus IB plus IC. That current is V1 minus V2 over I1 over 1, plus V3 minus V2 over 1, plus 0 minus V2 over 50, is the current, C dV dt. That's the same for all the nodes. Any given node then has the following equation. The voltage at node I will be a function of the adjacent nodes with plus 10, and the ith node will be a factor of minus 20. Except for the last node. There's only one resistor attached to the last node, so that equation is slightly different. So in state space, what the system is going to look like is this for the A matrix, minus 20.2 on the diagonal, 10 on the off diagonals, with the exception of this last guy. The B matrix, this extra 10, actually comes over to the input. It's right there. And the C matrix is what you're measuring. Here we're measuring the last state, state 10, so there's C and D. input the system into Matlab as state space ABCD. And if I want to say what's the factored transfer function, there it is. Again, way faster than you could ever do it by hand. For mass spring systems, state space also works, but it's slightly different. Here we have a two-mass system. The energy states would be kinetic energy and potential energy. Each mass has two energy states. Two masses makes it a fourth-order system. If I use the analogy of current is admittance times voltage, force equals mass times acceleration. If force is current, voltage is displacement, then admittance would be your ms squared for masses, ks, or k for springs, bs for friction. I can then redraw this as a circuit equivalent. Here you've got your ground. I've got two masses with 2 degrees of freedom. Each one has a displacement, so I've got two node voltages, x1, x2. Each mass goes to ground. That's Einstein's theory of relativity. The inertia of a mass doesn't depend upon any other mass. In fact, it doesn't really care if another mass exists. Then add the rest of the elements. Between node 1 and ground was friction. Between node and ground was a spring. There was a force being acting on node 1. Between nodes 1 and 2 was the friction and spring. Between node 2 and ground was the spring and friction and a mass. I can now write the node equations, noting that these are admittances rather than resistances. When they're admittances, one way to write the node equations is it's all the admittances attached to the node times x1 minus the admittances between nodes times x2 is the current to the node. That's this equation. Add node 2 is the admittances attached to the node times x2, that's these guys, minus the admittances between nodes times x1 is the current to the node, 0 in this case. So I've got my two equations that describe the equations of motion. Solve for the highest derivative, put in matrix form. Here it's slightly different. When I solve for the highest derivative, that'll be s squared x1, s squared x2. This is where the equations are that we just calculated. I get an extra two states. The energy is position for potential energy, velocity for kinetic energy. The derivative of position is velocity. So the first two rows is just a zero matrix, identity matrix, that tells you that these states are position, velocity. Net result is you get, for two masses, a fourth order system. Once I get this, I can throw it in Matlab. In Matlab, once you throw in numbers, here's your A matrix, B matrix. Your C matrix is what you're measuring. If I'm measuring state x2, I'll pull off the second state. Input the system in Matlab. So there's your A matrix. Here's your B matrix. I'm looking at state x2. In Matlab, input it as SS. And once I have the system, I can tell you what are the zeros, poles, and gain. And that gives you, here's your transfer function. So that should be enough to let you input systems into Matlab in state space form. The trick, though, is just coming up with your ABCD matrices.